Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning. So today I would like to post a video, okay, video lecture under chapter 4. Okay, chapter 4 equal area criterion. Okay, so if you read here from the last class, okay, from the previous class, so we have learned about what's the swing, how we get the swing equation, right? So you can refer back to the previous video that I had submit to you through the WhatsApp. So today we will discuss the equal area criterion. Okay, why equal area criterion is important. So actually from equal area criterion, and then from the what we call the power curve, okay, power curve. So we can identify the stability of a power system. So here the accelerating power is in a swing equation. We'll have the sign term. So therefore swing equation is a non-linear, right? Non-linear differential equation, and obtaining its solution is not simple due to the non-linear differential equation. So quite hard to what we call to analyze the stability of the system. But so we can use the equal criterion to identify the stability of the system. So here for two machine system and one machine connected to infinite bus bar, okay, it is possible to say whether a system has a transient stability or not without solving the swing equation. So we don't need to solve by using the swing equation, but we try to solve using the equal area criterion. So such criteria which decided the stability make use of equal area in a power angle diagram. So this power angle diagram, okay, so we can see later what is the power angle diagram, and hence it is known as a equal area criterion. From the power angle diagram, so we will use the equal area criterion to identify the power system stability. So thus is a principle by which stability under transient condition is determined without solving the solving equation, but makes use of areas, okay, but make use of area in power angle diagram. So what I mentioned before, so now it is called the equal area criterion. So here from the figure 3, it is clear that if the motor angle, okay, sigma oscillate, then the system is stable. For sigma to oscillate, it should reach the maximum value and then should decrease. So, okay, for the system to be stable, okay, the sigma should reach a maximum value and then should decrease. So from the figure 3. So at the point the sigma over dt is equal to 0, become of damping inherently present in the system, subsequent oscillation will be smaller and smaller. That's why the sigma change if at one instant of time this sigma equal to 0, then the stability is ensured. So this is how we what we call we can see from the power angle diagram. So the how the sigma will be oscillate, but because at the one the this sigma over dt, okay, the sigma over dt here. So supposed to be the value of d sigma over dt becomes smaller and smaller. So one it gets smaller and smaller, and then the stability can be measured. Okay, can be measured. So you can refer to the figure 3. Okay. So once the sigma over dt to become 0, okay, smaller and smaller, and that one equals to 0, okay, so to 0 angle lah. Okay, the string equation for the alternator connected to infinite bus bar is PS minus PE. So we can multiply both sides by the sigma over dt, so we get this equation 19. Okay, this equation 19. So thus you get once you integrate equation 19 here, and then you get the equation 20 here, right? So before the disturbance occur, sigma O for the top angle at that time, d sigma over dt is equal to 0. As soon as the disturbance occurs, the sigma over dt is no longer 0 and sigma will start changing. So top angle sigma will is to change. The machine will again be operating at synchronous speed after a disturbance when the sigma over dt, or when so you integrate the from the sigma O. Sigma O is the initial sigma to some value of sigma. You integrate 2 PS minus 3 divided by M. This sigma is equal to 0. So this example, okay, and then you get a equation 20. If there exists a top angle sigma for which the above is satisfied, then the machine will attain a new operating point and hence it has a transient stability. So the machine will not remain at rest with respect to infinite bars at the first time when the sigma is equal to 0, but due to the damping present in the system during subsequent oscillation, maximum value of sigma keep on decreasing. So therefore, the fact that the sigma has momentarily stopped changing by taken to indicate the stability. So this is how the power system stability, so we can see from the equal area criterion, but the important parameter in equal area criterion is the angle, okay? The angle sigma. Okay? So later we can see the what we call the example. Okay. So here this one example to explain so how the angle will be changed with respect to the time. Okay, how the sigma d sigma with respect to the dt. So the sigma over dt mean once how the sigma will be changed with respect to the time. So from this figure, okay, from this figure 4 here. So what we can see is a sudden load increase on synchronous motor. So what happened when the sudden load increase on synchronous motor? That is considered a synchronous motor connected to an infinite bus bar. So here you have okay, motor will be motor is connected to the infinite bus bar. So we can see. So this one is what we call the schematic diagram of the motor. So here is from here E is equal to V minus I times Jx. And then from here we can draw the Phasor diagram. This is the Phasor diagram. Okay, so here you can see the electric power. Okay, the electric power PE is equal to EV over X, EV over X sine sigma minus P max sine sigma. Okay, P max minus sine sigma. So here, so this your input power PE is equal to P max sine sigma. Okay, here. Okay, so here what you can see is that, this is the initial angle here. The initial angle. Okay, so PO, so A represent, point A represent the what we call the initial power, PO. So we can go through the next slide here, supposed to be. Okay, initial output. So the following changes occur when the load is increased suddenly. Okay, when the load is increased suddenly. So point A here, from this figure. Okay, so from this figure, point A. Okay, so point A, we refer to the point A here. Initial condition. So input is equal to output. The one is the PO. So omega is omega S and sigma is sigma O. Due to sudden loading, output PS, output more than input. So the omega will be decreased from omega S and sigma will be increased to omega O. So once the output is less than the input, okay, output is less than input. So what happens is the omega will be decreased from omega S. But what happened to the angle sigma is the angle sigma will be increased from sigma O to sigma S. Okay, to sigma S, from sigma O to sigma S. So between A and B, output less than input, rotating mass starts losing energy, resulting deceleration omega decrease. Okay, due to the output more than input, so omega will be decreased. So what happens is the sigma will be increased. So sigma will be increased from A to B. The sigma will be increased from the sigma O to sigma S. But so what happened to point B? At point B, output is equal to input. So at this point, omega is equal to omega min. So which is less than omega S. So the sigma is equal to sigma S. Since omega is less than omega S, the sigma continue to increase. Okay. The sigma, the angle sigma continue to increase. So means so you have understand at point A. So what happened at point A and B, and then what happened at point B, and then what happened to the point C? Okay, at point C. Okay, so between B and C here, so what we can see is the input more than output. Rotating mass starting gaining energy. Okay, acceleration. So omega starts increasing from minimum value but still less than omega S, and then the sigmas continue to increase. So what happened to point C here? In point C here, input more than output. Okay, so before that output more than input, and then omega is equal to omega S, and then the sigma is a sigma M. There is a acceleration, which is omega is going to increase from omega S, means sigma is going to decrease. from sigma m. So between C and B, input more than output acceleration, so omega increase and sigma will be decrease. So point B, input is equal to output, omega is omega max, so sigma is equal to sigma s. So since omega is greater than omega s, sigma continue to decrease. So what happened here? Okay, how the angle sigma will be changed with respect to the time. Okay, with respect to the time. Because of a damping present in the system, subsequent oscillation becomes smaller and smaller, and finally B will be the steady state operating point. So from the interpretation of the equal area here, what we can see is from the equation 21, the condition for stability. Okay, so the condition for stability. So the angle is equal to 0 is equal PE d sigma. From this equation, sigma O PS minus PE. PS minus PE. PS minus PE. So you can see here, sigma S to sigma M, sigma O to sigma M. So we want to calculate how we calculate the area in one and area A2 here, right? So sigma O to sigma M PE d sigma is equal to area sigma O ABC sigma M, and sigma O to sigma M PS area sigma O A D E. Where is A D E? So I cannot A D, okay, A D E A D E A D E A D E. So you can go through this one. So that's for stability, area sigma O ABC sigma M is equal to area sigma O A D E sigma A. So this part lah. Okay, this part. So subtracting area delta O ABE sigma M from both sides, ABE from both sides on both equation, and then we can get A2 is equal to A1. So A2 is equal to A1. Okay. Figure 5 shows three different cases. The one shown in case A is stable. Case B indicates critically stable, but case C fall under unstable. So the one is stable, the one is critical stable, the one is unstable. So that the area A1 and A2 are obtaining by finding the difference between input and output. Input and output. Right. Okay, so here you have one example here. Okay, one example here. Okay, one example here. You have a synchronous photo having a steady state stability limit to 200 megawatt. Is receiving 50 megawatt from the infinite bus bar. So find the maximum additional load that can be applied suddenly without causing instability. So here referring to figure 6, for critical stability, A2 is equal to A1. So which is if we put here, okay, A200, we mean the input power. Okay, 200, the maximum lah. Receiving at 1. Here, so PE sin sigma O is equal to 50. This example, sigma O is the sine minus 1, 50 over 200, 0.25 radian. So further 200 sin sigma here is equal to PS, adding area ABCDA to both A1 and A2. Both A1 and A2 are equating the result area. And then we can get here, but okay. The above equation can be solved by trial and error method. So using linear interpolation between second and third point, so we get delta S 0.927 region, thus PS is here. So maximum additional load possible is 109.96 megawatt. This is the maximum additional load. Okay, if you add more than 109.97, means your system become unstable. So this is the maximum load that you can add. Okay, to ensure your power system become stable. Okay, so about this case, opening of one of the parallel line. When a generator is supplying power to an infinite bus over two parallel transmission lines, the opening of one of the line will result in increase in the equivalent reactor and hence a decrease in the maximum power transfer. So because of this, depending upon the initial operating power, the generator may lose the synchronism even though the load could be supplied over the remaining line under steady state condition. So consider the system shown in figure 7 here. So power angle diagram corresponding to stable and unstable condition are shown in figure 8. Okay, so this is the electric output power to line, and then electric power one line. So from here actually your A2 is equal to A1, that one is stable, but A1, A2 A2 more than A1, then become unstable. So what we want to know here is, so what happens to the stability of our system when the fault occur in transmission line, right? So the short circuit occurring in the system, often causes loss of stability, even though the fault may be removed, but isolating it from the rest of the system is a relatively short time. A three-phase fault at one end of a double circuit line is figure 9A, okay, figure 9A here. So we can reduce as shown in figure 9B. So it is to be noted that all the current from the generator flow through the fault, and this current IG lag the generator voltage by 90 degree. So thus the real power output of generator is zero. So normally the input power to the generator remain unaltered. So therefore, if the fault is sustained, the load angle, the sigma, will be increased indefinitely, because the entire the input power will be used for acceleration. So this may fault result in unstable condition. When the three-phase fault occurring at one end of double circuit line is disconnected by opening the circuit breaker and at both ends of the faulted line, power is again transmitted. So if the fault is clear before the rotor angle reach a particular value, the system will be remain stable. Otherwise, it will be lose stability as shown in figure 10. So here pre-fault output power, post-fault output power. So pre-fault, I mean before fault occur in the system, and then so what happened when the fault uh, totally clear from the transmission line, and then actually you can see the magnitude of the power here is decreased from the pre-fault to the power fault, right? So here what we can see is a delta C less than delta CC here. Delta C less than delta CC here. So delta CC is the critical clearing angle. Critical clearing angle. So what we can see here, that we can note that the error N1 and A2 are obtaining by finding difference between input and output. So when a three-phase fault occurs at some point on the double circuit line other than on the extreme end, it shown in figure 11A here, there is some finite impedance between the paralleling bus and the fault. So therefore, some power is transmitted during the fault, and it may be calculated after reducing the network to a delta connected circuit between the internal voltage of the generator and the infinite bus as shown in figure 11. Okay, figure 11. So here what we can see, the power transmitted during the fault is equal to EG times EM divided by XP. So normally XP the total resistance. So after you simplify the circuit, figure 11B. Okay, so stable, critical stable, and unstable condition of such system are shown here. Okay, so that one is pre-fault, means before fault. Okay, before fault. Post fault, after fault, and then that one is a during fault. During fault. So after fault means after you clear the fault on the power system or transmission line. Okay, so what we can see here, delta C less than delta CCI. A2 is equal to M1. So that one is become stable condition. And then the next is one we call the A2 is equal to A1. That one is the critical stable. So what happened for the unstable, we can see A2 less than A1. So this is how we determine the stability of the system. So example 2 here, okay, example 2 here. So I hope you can go through this example 2. Okay, example 2 during for pre-fault condition. So you have to know pre-fault condition, and then the next is the during fault condition here. Okay, during fault condition. Okay, this is the post-fault condition. So from three conditions here, so we can determine the power, okay, the power output, okay, the power output PE. So we can simplify here. What we can see is, okay, what we can see is this one. For the pre-fault, so we can determine the magnitude is 1736. But during the fault, the magnitude or the power output will be decreased drastically from 1.736 to the 0.418, and then after we clear the fault on the transmission line, and then the magnitude of power output become increased back to 1.225. Okay, 1.25. So they were is PM1, PM2, and then PM3. So okay, one is expression for critical clearing angle. Okay, so why critical clearing angle is very important. So the critical clearing angle sigma CCC is important because we have to know what is the what is the critical angle that we need, okay, to ensure that the power system in a stable condition, right? So consider the power angle diagram shown in figure 1.3 here. Okay, pre-fault output power, post-fault output power during output power. So from there you can calculate the error A1 and then error A2. So at the end what we can get is the last equation. Okay, the last equation here. Thus, the angle is given by this one. So here the angle are in radian for the seats. So we can create the delta O and delta M. So example 3 in the power system described in the previous example, if the generator was delivering 1 unit PU just before the fault occurred, calculate delta CC. PS is equal to 1, and then what we can calculate is critical clearing angle delta CC is equal to 52.331. Right? So, so I hope you can take note. You can read and then understand how we calculate the critical clearing angle. So this is the second topic. So the next class is step-by-step solution of obtaining a swing curve. So I will discuss the last topic. The last topic is step-by-step solution of obtaining swing curve. So I hope you can understand. Okay, you can understand all these things. So okay, that's all. Thank you very much. So I will I will send a few notes, okay? A few notes to class about how the example the how critical you calculate critical clearing angle delta CC and so on. So hopefully you can study by yourself to until this slide. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Mana yang lain? So can I start now? Boleh tak? Okay, cek mana? Okay, so Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Waalaikumsalam. Okay, so the topic today is under chapter 4. So this is the last chapter in the EPO553. So can you see my slide? Table lah betul tak? Yang tu yang kita nak. Yang TMB hantar. Kita tak nak TMB bantu. So stability of a power system is its ability. It is ability to return to normal or stable operating condition after having been subjected to some form of disturbance. That one we call as a stability. Stability of a power system is an ability, kebolehan lah. Kebolehan kita punya power system untuk kembali ke keadaan asal ataupun beroperasi dalam stable punya condition selepas mengalami satu gangguan. Itu dah dibeli lah. Kalau kita nak faham lagi detail kan. So ability to return to normal or stable operating condition after having been subjected to some form of disturbance. So disturbance means, so you have a lot of causes, and then maybe due to the lightning, due to the fault, fault and so on. So conversely, instability means a condition denoting loss of synchronism of falling out of step. Okay, jadi dalam keadaan mana sekarang? Yang dikatakan instability maksudnya keadaan step, but also on the type of fault, location of fault, clearing time, and the method of clearing. So kat sini dia kata sama ada sistem stable ataupun semasa berlakunya fault, dia bergantung bukan saja pada sistem itu sendiri, tetapi juga bergantung kepada type of fault. Yang pertama, fault punya lokasi fault, atau masa untuk clearing time, masa untuk kita clear the fault, and then the method of clearing the fault. So cara untuk kita clear the fault, masa untuk clear dan cara untuk clear the fault. So this is the best statement here, right? So here, okay. So this is very important. So you have to know. So transient stability limit is almost always lower than the steady state limit, and hence it is much important. So transient stability limit depend on the type of disturbance, location, and magnitude of this disturbance. Right. Ni the information berkenaan dengan disturbance and so on. Right. So the next slide, what? Okay, review of mechanic. Okay, review of mechanic. They only be referred to the turbine operation lah. Turbine operation. So transient stability analysis involves some mechanical property of the machines in the system. So after every disturbance, selepas setiap kali berlakunya gangguan, the machines must adjust the relative angle of their rotor to meet the condition of the power transfer involved. Okay, yang ni sebenarnya kita bincang kat mana dulu? Okay, this one kita bincang dalam automatic generation control. Yang kita study dia punya what we call berkaitan di antara apa? Masih ingat lagi? Kita ada, yang penting sebenarnya kita nak adjust apa? Frekuensi kan? Betul tak? Ingat lagi? AGC? Hello? Hello?
Ingat saya, ingat lah.
So frekuensi dia akan berubah ikut apa sebenarnya? Okay, yang kita study P1 plus P2 is equal to P power demand kan. Bila power demand increase, apa jadi pada frekuensi? Frekuensi jadi apa? Frekuensi kan jadi drop.
Demand naik, frekuensi turun saja.
Kita refer pada kita punya ni. Ingat kita Kamu kira ni kita punya frekuensi, ni kita punya power demand, betul. Okay. So after every disturbance, the machine must adjust the relative angle. So maksud sekali apabila berlakunya perubahan dalam yang dikatakan power transfer involved ni, yang ni lah. Yang ni bila berlakunya perubahan. So bila berlakunya disturbance, automatic machine will be adjust the relative angle of their rotor. So rotor angle ni memainkan peranan yang paling penting sebenarnya di dalam proses kita nak transfer sama ada kita nak increase the power ataupun kita nak decrease power, ataupun kita the way kita nak transfer kita punya power pada kita punya power system from generation to transmission. So the problem is mechanical as well as electrical. So bila berlaku nanti dua benda yang paling penting akan melibatkan masalah di dalam mechanical dan juga electrical, right? So dia punya review of mechanical. So kalau kita betul-betul baca kat sini, kita nampak dia punya